Okay, we're going to switch over to our last presenter, Arjun Singh from the University of California, Berkeley. Arjun received his BS in Electrical Engineering and Computer Science from the University of California, Berkeley. He is now a Ph.D. student and an NDSEG fellow at Berkeley, where he works on robotics and computer vision. The title of his presentation is Apprenticeship Learning for High-Performance Helicopter Flight. For many robotic systems, human operators still significantly outperform autonomous operation. Apprenticeship learning is a new approach to high-performance robot control based on learning for control from ensembles of expert human demonstrations. In this talk, Arjun will present the theory of the apprenticeship learning algorithms, as well as experimental results in autonomous helicopter flight. Apprenticeship learning has enabled the most advanced helicopter aerobatics to date, including maneuvers such as chaos, tic-tocs, and auto-rotation landings that only exceptional, expert human pilots can fly. Arjun, thank you.
Thank you. Okay, so yeah, I'm Arjun Singh, and my advisor at Berkeley is Peter Abil. So the work I'll be describing today was started at Stanford, where my advisor collaborated with Adam Coates, Andrew Ng, Morgan Quigley, and Tim Hunter. And then when he became a professor at Berkeley is when I started working on the project, where we collaborated with Jay Tang and Nimbus Gohausen. Okay, so what makes this a hard problem? So first off, the dynamics of helicopter flight are unstable. And what that means is that when a pilot is flying a helicopter, if they took their eyes off the helicopter for more than a couple seconds, it would probably just crash. The pilot has to be continuously providing controls and continuously responding to what's going on with the helicopter. On top of that, helicopters are nonlinear and have complicated dynamics. So we can't model everything that's going on with the helicopter. There's a complex airflow going on. There's coupling between different parts of the helicopter. There's the dynamics of the blades that flex as it flies. And furthermore, all we get are noisy estimates of the state of the helicopter, including the position, the orientation, the velocity, and the angular rate. And for some maneuvers, we also have sensors for the blade and engine speed. Okay, so even though helicopter flight is a very challenging problem, there have been some success stories. And so some examples are listed here on this slide. The control techniques used for these success stories, I guess, are inner and outer loop Ph.D. control. And sometimes those are hand-tuned, sometimes those are automatically tuned. There's H-infinity control, LQR, and many other techniques. However, these successes have only been in the hover and forward flight regime. So either the helicopter is hovering or it's flying forwards. It's not doing anything more complicated than that. So here's an example result of that. So this was achieved by Andrew Ng and his collaborators in 2004. And this isn't an image. The video is actually working here. This is just a very, very good hover. And so this is great, especially for an autonomous helicopter. This is really, really good for a human. So let's see another example. This is also done by Andrew Ng and collaborators. So you see it hovering. Then if you look more closely, you'll notice that it's actually hovering upside down. Okay, so now we've shown two impressive examples of what's been done. And so now, we can hover it upside down. So what about flipping it upside down? So in that video, what happened was the pilot flipped it upside down and then handed control over to the computer. And the computer did a great job of hovering. But the computer couldn't actually flip it. And so they decided to use the same techniques they used for the inverted hover to try to get it to flip. And so to do that, they first had to specify a trajectory. For hover, the trajectory is very simple. You don't want the helicopter to move. For flipping, we have to say, okay, we want it to stay in place and flip upside down, and maybe we'll do that a couple times. Okay? And so let's see what happened when they tried to hand engineer a trajectory and use the same techniques to follow that trajectory. So you see the helicopter flip. It's moving kind of a lot, more than you might want. And then it's taken to its limits. The engine dies, and the helicopter crashes. And like I said, the technique used here was essentially the same thing that was used for those hover examples I showed you. And so it's clear that the same techniques don't work here. And the way the model was generated here was a very typical way of finding a model for helicopters. And so what you do is you take the control inputs, you sweep them at a range of frequencies, and you run a regression to get the model out. And I'll go into more detail about that later. But there's nothing that fancy going on here. Just want to say that those methods don't work out of the box. Okay, so what's different? So we're talking about aggressive non-stationary regimes here. And so what success stories were there in these regimes? And so perhaps the only real success story before our work was by Gavrilets, Martinos, Mettler, and Ferrone in 2002. And what they did is they had their helicopter autonomously fly 3 maneuvers: a split S, snap axial roll, and a stall turn. And if you're not familiar with those maneuvers, you'll see video of some of these later. And how do they do this? So what they did is they had their human expert fly these maneuvers. Then they meticulously analyzed what the human expert was doing, how the human compensated for different types of error, and they hand-engineered controllers to emulate what the human does. And it worked very well, but it was extremely time-consuming. And there's a reason that they stuck to these 3 maneuvers and they didn't go to the full range of what the pilot could do. And that's simply that there wasn't enough time. So we're going to start with the same learning point here with our method. We're going to have a human expert give demonstrations. The difference is that we're not going to have to hand-analyze anything. The algorithm will do that for us. So the human flies something, and then we can fly the same thing. And what I'll go through in this presentation is I'll show you that this method generalizes to a wide range of aggressive maneuvers. It can execute them in rapid succession. And like I said, we start at the exact same point as these hand-engineered controllers did. Okay, so what's so different about stationary flight versus aggressive flight? Why is this so much more difficult? So with hover and the stationary flight regimes, it's much easier because you can focus on that single regime. And that enables you to do things like collect a lot of data. So that data I told you that we collected with the frequency sweeps, we could just do that for 10 minutes, an hour, 3 hours, whatever, and it's all for the exact same regime, right? And that lets you get a very, very good model for that regime. So what are we collecting? We're collecting the control inputs that the pilot is giving, and again, the position, orientation, velocity, angular rate. And then we build a model and a model-based controller from those. So the model-based controller actually works in these regimes because we have enough data and because it's not changing. So why can't we do that technique? Why can't we use the same technique for the aggressive flight regimes? So first off, you just can't collect that much data to get that high fidelity of a model for the entire flight envelope that you're considering, right? Before, we were only considering the hovering situation, and now we want to consider doing flips and stall turns and loops and all those things, and we just don't have, it's infeasible to collect enough data in a reasonable amount of time. So the second challenge that I mentioned kind of is building a dynamics model. And what we'll find later is that the answer isn't to build a single dynamics model that works for the entire helicopter everywhere. It's actually a non-parametric model that's different for each trajectory. And we'll go into more detail about that too. Sorry. Okay. Another challenge is that it's not even clear what the target trajectory is. Okay. So with hover, like I said, you just say you don't want it to move. So for example, you might want it to do flips. And so you might think, oh, it's easy. I just want it to do flips. So it means just rotate in place. But you can't just rotate in place. You also need to supply a vertical thrust that allows the helicopter to stay in the air. And so now there's this trade-off between flipping in place and providing enough thrust so you don't crash. And what's the right trade-off? How do you make that trade-off? Right? So we need to actually specify the full trajectory, all the positions and orientations throughout the entire flight, such that it's actually feasible. And like I said, I already mentioned the dynamics model. Okay. So the outline is, we'll talk about how to learn the target trajectory, and then I'll go into how to learn the dynamics model, and I'll show you some results for both of those. Okay. So as I mentioned, it's very difficult to specify these trajectories by hand. The required format is a position and orientation over time, and these positions and orientations have to satisfy the helicopter's dynamics. If they don't, then you can't fly it. That's the definition. So what our solution is, we're going to collect demonstrations of the desired maneuvers. So we'll have the pilot fly 5 stall turns of roughly the same height and same parameters and everything. So we just tell the pilot to fly the same thing 5 times. And the challenge now becomes to extract a clean target trajectory from these many suboptimal and noisy demonstrations. Right, so the pilot's not perfect. I mean, they can get these things to fly well, and they're great, but they're not going to fly the same thing 5 times. You can't do that. And so none of those 5 examples is going to give us are exactly what we want to fly. So what we have to do is kind of average them together and take out the good parts and leave out the bad parts. So let's get an idea of what it exactly is that we're asking for here. So here's a video that shows 6 demonstrations by our pilot. And these are just graphical replays of the data that we logged. And you'll notice that the pilot is actually flying essentially the same maneuvers, but there's a lot of variability between them. They're flying at different rates, different sizes, different positions. And so now our challenge is to take all these things and output a single trajectory that is a better version of all of these that we want our helicopter to follow. So here's the key idea of this approach. So underlying it is essentially a hidden Markov model, where we have hidden states. And the hidden states here are going to be the trajectory that we want the helicopter to follow. Okay? So at the time 1, it'll be the starting state of the helicopter. At time 2, it'll be the next one, and so on, specifying the entire trajectory. And we don't know what they are, right? That's what we're trying to find out. So we're leaving those empty for now. What do we have, though? We have 2 demos of 2 examples of what the pilot flew. We have a dynamics model, which essentially says what the relationship between these hidden states have to follow, right? You have to be able to get to state 2 from state 1, otherwise the helicopter will crash. And so now looking at this, we've got a bit of a problem here. If you'll notice, demo 1 and demo 2 aren't of the same length. And so what do? Are we just going to average them? Are we going to pick one of them? How do we pick the right length for our target trajectory? So to solve this, what we do is we align these trajectories to the hidden trajectory. And you might wonder how we do that if we start with a blank hidden trajectory. So what we do is we just subsample one of them as an initialization. So we took the first demo, we subsampled it, and now what we're going to do is use an algorithm called dynamic time warping, which lets you efficiently align time series, and will align the hidden trajectory that we just initialized to each of the demos. So what this graphic here is showing you is, for each of the demos, what's the state that's most closely corresponding in the hidden trajectory? Okay, so now we've got each of the demos aligned to our hidden state. What do we do now? So now we have 2 observations at each time of the hidden state. And so what we do is we run probabilistic inference, and we're going to re-estimate what the hidden state should be. Okay, so we set it to blank again, and we're going to re-estimate what it should be from these demonstrations. And to do that, we use an extended Kalman filter smoother. If you're curious about the details, you can ask me afterwards. And so you've noticed that we filled in a better trajectory that used the data from both of these demonstrations. And so you might be wondering how this could work. Like, we initialize it kind of arbitrarily. How does that work? And the answer is that it doesn't work if you just do it once. You have to iterate. So now we have a new hidden trajectory. We can realign both of the demos to this new hidden trajectory. Okay, so now we have new alignments. And then we can re-estimate the hidden trajectory the same way we did earlier. Right? So now we've estimated again. And we repeat this process until it converges, which means that things don't change. And typically, we get good performance after maybe running 2 to 5 iterations of this. And this is all done offline, by the way. This isn't being done online, so this is kind of fine because we're generating a trajectory at this point. Okay, so let's see what the results of that look like. So these are the same 6 demos I showed you earlier, except now our algorithm has aligned them, and we've inserted a new demo, which is the white helicopter. And you'll notice that it really is kind of the ideal version. It does capture the pilot's intent of what he was trying to fly. Obviously, the pilot couldn't fly this perfectly because there's a lot of variation, and it's a very hard control problem. But we can extract his intent. And this is completely automated. Once you have demonstrations, you feed it to the algorithm, you get out a target trajectory. Okay, so let's look at some results here. These are demos that the pilot provided. And you'll notice that they look very different, right? There's a lot of variability here. So the black one here, the black dotted line here is what the algorithm learned. And you'll see that it is a much, much cleaner version of a double loop than what the pilot could fly. Okay, so we've now gone through how to create a target trajectory. Now we have to learn how to follow that target trajectory, right? So this is just the first step of the problem. If we use the same methods we did before, the helicopter would still crash, as you saw. So this is the baseline dynamics model. And I'll go into some detail about what each of these terms mean, just so you can have some background knowledge about this. So the first expression here, okay, let me take a step back. So U, V, and W are the velocities in the helicopter's frame. So U is the forward velocity, V is the sideways velocity, and W is the vertical velocity. Sorry, U, V, and W dot. Okay. And then P, Q, and R are the angular rates. So it's roll, pitch, and yaw. So let's look at what these terms mean. So this first term for U dot consists of V and R. So what this is saying is that if the helicopter is moving sideways and then it rotates along its vertical axis, that sideways velocity will turn into forward velocity. Okay, so this is just predicting what's going to happen if we're moving in a direction and we rotate a little bit. Second term is the same thing, except it's in the vertical direction. Right? So if the helicopter is moving upwards and then it pitches forwards, it'll start going forwards. And you've got similar terms for both of these, for all three of these, U, V, and W dot. The last term here is a drag coefficient, essentially. Sorry, the last term is drag coefficient. And there's also a gravity component, which is just the component of gravity that's aligned with each of the axes. Right? So you've got the forward, sideways, and vertical axes. In addition, for the vertical axis, it's not simply a drag coefficient, but we also have a control input that exerts influence on this axis. So I collective is a control input. So if you imagine the helicopter is hovering and you increase the collective, it'll go upwards, essentially. Then there's, again, the same drag coefficient. And lastly, there's this offset term. And what the offset term, offset term represents is simply that the controls aren't perfectly centered, and so you need to be able to compensate for that. And so although CU, CV have one number each, CW is actually a vector that contains three numbers. Okay, so for PQ and R, it's very similar. We've got one control input for each of these axes that controls how fast the helicopter will rotate in each axis. Similarly, we've got a drag term and an offset to compensate for the fact that the controls aren't perfectly centered. Yeah, so we don't model any airflow or any of that. Yeah. And we'll get into how this could possibly work soon. Okay, so let's look at what happens when we're using this model. So what this plot shows you is the x-axis here is time, and the z-axis is error. So what we did is we took our model, we predicted what the helicopter would do in response to our control inputs, and we compared it to what it actually did. Okay? And so you notice that the errors are huge, right? So at this point, that's roughly 3 Gs of error here. So it's like 30 meters per second squared of error here. And so if you tried to fly a helicopter using this model, which you saw earlier, essentially, it crashes. Okay? Yeah, 3 Gs of error at that point. So there's a key observation that helps us deal with this. So here we've plotted the actual error for a few different flights. And if you look, there's a pattern. And maybe you have a hard time seeing it at this point. But let's see what happens when you align the trajectories using the algorithm I described earlier. Now the pattern is much clearer. And so there's a lot of consistency in how our model is off for a given type of trajectory. And so as a side effect of the alignment algorithm described earlier, we have a way of aligning these errors. And so this will give us some insight into how we can use these errors to get a better model out, essentially, right? So now we're saying that we've got these trajectories we want to follow. We know that it's going to be off by 3 Gs at this point in the trajectory. And so we can just kind of add that in. Right? So if we follow the same trajectory repeatedly, the errors are consistent over time after the alignment of the data. And so why is that? Why does that work? And this gets to your question a little bit. And that's that we think what's going on here is that there's a few unmodeled variables that we just don't have sensor data for. And we think that the net effect of those variables is the same for the same flight over time. Right? So the airflow around the helicopter, the actuator delays, and many other variables that we're not modeling. So as you saw in that plot, that kind of holds, right? The net effect is roughly the same for different flights. And the intuition here is kind of the same as what human pilots have with muscle memory. It's not like the human pilots know the airflow around the helicopter. They don't have any sensors, so let them do that. It's that they know how the helicopter reacts when they fly the same trajectory over and over again. So what we're doing then is learning trajectory-specific local models. So we've got data that's aligned in time. We can weight by the time to exploit the repeatability of the unmodeled variables. So what we're doing is, at each point in the trajectory, we're trying to say how far off our model will be, the baseline model will be. And what we do is we take a window around each time, essentially, and we say that we're going to average over that window. And it's not quite that simple. We use a weighted average that doesn't actually have a sharp cutoff. And what this gives us is a model for each time for each maneuver. So let's see what that does. Before I go into that, I'm going to talk about our experimental setup a little bit so you have an idea of what data there is and what exactly is going on. So the helicopter's pretty much off the shelf. Our human pilot built it for us, but there's no modifications to the helicopter itself. We put on an inertial unit, Microstream 3DM GX1. It provides data at 333 hertz. It gives you magnetometer data, gyro data, and accelerometer data for all three axes. For some of the later examples I'll show you, there is a RPM sensor, and so that tells us the blade speed. And we've also got sonar on the helicopter, so we can tell how far the helicopter is from the ground. We've also got these offboard cameras, and what we do with offboard cameras is we track the position of the helicopter. And you might wonder why we don't use GPS, and the reason is that when the helicopter is flying as fast as it does, the GPS starts to lose its signal lock. Also, when the helicopter is flipping, you might imagine that it also has trouble keeping a signal lock, right? Because now the helicopter is in between the satellite and the sensor. The computer is off board. It's not on the helicopter, and the only reason for that is essentially weight considerations. And also, if it crashes, we don't lose the computer. And the computer is running an extended Kalman filter, and what that's doing is it's taking in all of the sensor data, the sonar, the inertial unit, the cameras, and it's outputting the state of the helicopter, an estimate of the state of the helicopter. Also running on the computer is the receding horizon differential dynamic programming controller. And I'll break that down a little bit to give you some idea of what exactly that means. So what's going on with, what's the exact setup that's going on here? So we've got a controller that's sending signals to the helicopter at 20 hertz. How do we pick what controllers are sent? So this is where the receding horizon part of the controller comes in. What we do is we simulate for some horizon, in this case it's 2 seconds, what would happen if we sent a sequence of controls for those 2 seconds. So essentially, since it's 20 hertz in 2 seconds, we pick 40 sets of control inputs to give to the helicopter. And we pick the best 40 at the given time. And then we send the first one. And now it's a new time step later. And we rerun the process. We don't send the second time step from the 40 we just computed. We recompute a new set of 40. And then we send the first one of those 40. And we keep doing that until the trajectory is completed. And the reason for that is this lets us account for deviations from the trajectory that we might have encountered, right? Let's say the control that we sent wasn't the best control, actually. If we just sent the same thing we computed a second ago, or a tick ago, or a 20th of a second ago, then we'd be sending suboptimal controls, because now we have more information about where the helicopter is and how far off from the trajectory we might be. And so we found that 2 seconds is a good trade-off in computation time, because this lets us stay real time, which is obviously important, and accuracy. Okay, so just a quick recap of what exactly is going on. We collect the sweeps data that I described earlier to build a baseline dynamics model. Our expert pilot demonstrates the air show several times. We learn the target trajectory using the algorithm I described earlier. We learn a dynamics model using the other algorithm I described earlier. And this is the local dynamics model, right? This isn't the baseline now. This is the per-trajectory dynamics model. And then we find the optimal control policy for the learned target dynamics model. This is essentially the RHJDP controller. And then we fly the air show. And this process, I'll get to that in a second. After we fly the air show once, we can actually improve on the performance. And so, as you saw in the demos I showed you earlier, the pilot can't repeat a trajectory perfectly, right? However, when a computer is flying it and it doesn't crash, it can repeat the trajectory fairly well, actually. So once we have a good trajectory that's good enough to fly, it flies the same thing repeatedly. And so it might not look perfect yet, but it'll fly the same thing in the same imperfect way. And what we can do then is learn why it flew imperfectly and update the dynamics model, right? So we had some target trajectory. We flew it using the controller and dynamics model we just estimated, and it didn't work perfectly yet. And then what we're going to do is go back and see why it didn't work and update this. And we're going to iterate that like maybe 2 or 3 times. And in the end, what happens is it takes about an hour to learn a new trajectory. So this whole process, once everything is in place, takes about an hour. Okay, so let's see some results. So the helicopter starts off on the ground, it spins up its blades, it takes off and does this inverted takeoff. And you'll see the first 3 things are kind of the 3 maneuvers I described earlier that previous work has done. So the first 15 seconds shows you what all of the previous success in this area has been, and everything after that is completely new. So there's a split S, there's a snap roll, and here's a stall turn. And what a stall turn is good for is it's a quick way of changing direction. So loops, those are new, they weren't flown before. We'll do a stall turn, and this time we'll do it differently because we'll come out tail first. So the other stall turns would turn around at the peak. This hurricane is a fast backward flying cycle, essentially. So now we're going to do stationary rolls and stationary flips, and these are actually some of the hardest maneuvers. And the reason for that is that when you're flying in just a kind of a confined space, the helicopter is fighting its own airflow. And tic-tocs, again, are also some of the most difficult maneuvers for the same reasons. And we'll stop with the inverted hover. Okay, so thanks. So that looks very nice, but did it actually fly what we wanted to? So let's verify that. So the white helicopter is the target trajectory, and the black helicopter is the replay of what we just flew. And you'll see that they're pretty close, actually. And the position accuracy is essentially 1 to 2 meters. And that's even while flying under really high g-forces and high speeds. And it's, depending on what you think, you might think 1 or 2 meters is really good or not so good, but it's very, very good in this case. And if you ask a human pilot to fly this air show with an accuracy of 1 meter, they'd probably think you're crazy. And so it stays really close throughout the entire trajectory. So let's take a look at another maneuver. So this is called auto rotation. And this is an emergency maneuver that you might perform if your engine dies or if your tail rotor dies. And the idea here is that if your engine dies, it'd be nice to not lose the entire helicopter. And when your tail rotor dies, your engine might still be working, but your helicopter will start pirouetting uncontrollably, essentially. And in order to land it safely, you have to shut off the engine anyways. And so when you switch off the engine and you try to land safely, essentially what you're trying to do is you're trying to maintain high blade speed while you're high in the air in this area, and then you try to slow down the blade speed as you get closer. And so there's 3 phases in auto rotation landing, and this area up here where you try to keep the high blade speed is called glide. When you try to slow down, it's called the flare, and then there's the landing. And the way the landing works is essentially you hope that by the end of the flare, you're close enough to the ground to where you can just fall. And if you didn't do that right, then there's nothing you can do at that point. Okay, so this requires a different dynamics model. And as you might imagine, it's hard to worry about the blade speed if you have no idea what it is. And so the new dynamics model is going to actually introduce the blade speed, which we'll represent as omega here. And it just adds some terms to the dynamics model that depends on that. And so perhaps the most important is this one here. So before, this term was simply the collective control. And now we multiply it by the blade speed, right? So if your blade speed is low, then the collective has less of an impact. And that makes sense, right? I mean, now before your engine was actually running, and so it didn't matter because you could actually control the engine, and now you can't do that anymore. So the blade speed matters now. And so if you assume that the collective will have the same effect as it would at a high blade speed, you'd be in for quite the surprise, and you'd crash. And again, we do the exact same thing as before. We collect the same kind of data. There's no difference in the data collection. There's no difference in the learning of this model. It's still a simple linear regression. All that changes is that we added a few parameters. So here's how well this works. And so this is just showing you essentially the same thing I showed you before with the giant errors. It actually works pretty well in this case. And so the solid line is the simulation, and the dashed line is the flight data. And this is how well we can predict the blade speed. So we concluded from this that this was kind of good enough on its own to try some auto rotation landings. So let's see that. So this is the glide phase. And now it's flaring. And it lands. And this will loop a couple times, but just so you have some idea, we repeated this 35 times, and it was successful all 35. So is this kind of luck, or are we controlling this, or what's going on here? So let's see how accurately we were actually controlling the blade speed. So what we did here, while you're doing the glide, you can't avoid losing some blade speed as you fall. So what we do is we set a target of roughly 1150, and we set some target forward velocities and downward velocities, and we want to keep the helicopter level. And we see that the controller is actually very good at keeping it at that rate. At that blade speed. So what are some current directions with this work? So the work I described to you, one of the limitations was that every time you want to fly something new, you probably have to provide you 4 or 5 demonstrations of it. So can we do better? So let's say we have the pilot fly a 20-meter stall turn, and a 30-meter stall turn, and a 40-meter stall turn, and a 50-meter stall turn. At that point, can we ask an algorithm to give us a 25-meter stall turn, or a 35-meter stall turn, or a 22, or 27, or anything in between? And some preliminary work here actually shows us that you can, in fact, do that for trajectories that are close enough. And what happens is we input kind of these 5 demos, 20, 30, 40, 50, and we ask you for anything in between, and it outputs a target trajectory and a dynamics model that are good enough to fly. And the accuracy of these isn't going to be the same 1 to 2 meter. It's kind of more 2 to 3 meter, but it's still very, very good. So it's going to be better than just flying one of the 20 or 30 or 40 meter stall turns that you have in your library. Essentially, the answer is if you don't have the data, you can do better. It's better if you can collect the data and ask the pilot to fly these trajectories. But if you don't have it, we can design an algorithm that can do better. And so here's an example of a parameterized maneuver. And this is probably the most difficult helicopter maneuver that humans fly. And so it's called the chaos, for a good reason, in my opinion. And the helicopter pirouettes in place while flipping at the same time. And so to me, it's kind of amazing that it even stays in the air while doing this. But in this case, we've even parameterized it by yaw rate. And so we can say we want it to pirouette at a rate of 1 pirouette per second, and it'll generate a chaos that we can fly. Or we can say 1.5 pirouettes per second, and it'll generate a chaos that we can fly. So in summary, our approach leverages multiple expert demonstrations to, first off, infer a target trajectory, and second, learn better models along that trajectory for control. And this enabled extreme aerobatics at the level of an expert human pilot. And so now we can hopefully talk about how this might be applicable to the work that you're interested in. Thank you.